Welcome to Lecture 16, the Interstellar Medium and Star Formation. Assuming you've been with us for the first 15 lectures, you'll know that in the last several, we spent quite a bit of time talking about the Sun, and through the Sun, we learned about a large number of stars in the universe. As I have highlighted a number of times, the Sun is a pretty generic main sequence star. So everything that you've learned about the Sun, it turns out, or not everything, but the vast majority of that is going to be generally applicable to low mass stars. So we'll say more about that here shortly, but today we're going to take a step back, actually, and talk about the interstellar medium and star formation. So, we've spent a few weeks now talking about stars themselves and their properties and what fuels them and so on. But today we're going to go back in time a little bit and talk about how those things are made, how the stars form out of the interstellar medium, and what that interstellar medium is. So let's dig in. So as we said way back in the beginning of the course, you live in a galaxy, and that galaxy happens to be known as the Milky Way. As you probably know, there are a whole lot of other galaxies, both in our relatively nearby astronomical neighborhood and certainly throughout the universe. And there are a number of similarities that all of these galaxies have in common. And as we'll discuss, there are plenty of differences as well. But all galaxies are made up of the same stuff in general. And that stuff is stars, dust, and gas. The vast majority of the mass is in stars. As might not be surprising. And certainly we see most of the stars are what we see because they're the things giving off light. But there is this dust and gas that is going to form or forms what we're going to call the interstellar medium, and that's the topic today. So this interstellar medium is what it sounds like. Again, continuing on, with the beating of a dead horse that astronomers and physicists are not creative in naming things. The interstellar medium is the medium, which means the stuff, in between the stars. Okay, and that's all it is. So there are a number of cool pictures that are that have both stars in them and parts of the interstellar medium. Here's a great example. The Elephant's Trunk Nebula. As you can imagine, and I'll quantify this here shortly, the majority of the interstellar medium is very low density. Of course, when you say something is low, or small or large, it's always relative to something. But the interstellar medium is very low density relative to almost anything you would ever think of. Certainly it's much lower density than stars, it's much lower density than planets, right? It's mostly empty, okay? But it's not completely empty, and that's important, and that's what we're talking about today. So here's another example, the Orion Nebula. This is what we call a dense cloud of gas and dust. This one happens to be in the constellation Orion, and so again, not creative in naming things. It's a nebula in the constellation of Orion, and so we call it the Orion Nebula. So when we say, though, a dense cloud of gas and dust here, we mean dense relative to the interstellar medium. Okay, so again, the interstellar medium is really low density because interstellar space is mostly empty, but it's not uniformly mostly empty. There are parts that are more empty and parts that are less empty. And so nebula are areas which are relatively less empty than the rest of interstellar space. And so it's not, when we say it's dense, I don't mean dense relative to a star, because it's not a star itself, though there may be stars inside the nebula. But relative to interstellar space, it's dense, containing both gas and dust. Now these colors are not, well, they're not false colors, though if you just looked through a telescope in your backyard, you would probably not be able to make them out. But as we have seen throughout the course, you can tell a lot about what's in a star, or in this case, what's in a nebula, what's in the gas of interstellar space, by looking at the colors of light that you get. And so in this particular case, we see the traditional red line from hydrogen. So if we see red light, that's typically coming from hot hydrogen gas. Green light is a prominent oxygen emission line, so that indicates that some regions of interstellar space, or regions of the nebula where there is some oxygen. And then there's some blue light as well. That comes from hot stars, right? And quite hot stars. Remember, we've talked about the different classes of stars, which range from M-class stars on the cool end up to O-class stars on the hottest end. And you really have to get quite hot before blue is the dominant color. But it happens, they're out there, and so when you see blue light, that's where it's coming from. It's just coming from those very massive, very hot stars that we'll say more about a few lectures from now. And, you know, since when you signed up for this class, you probably did so with at least a little bit of a thought that you get to see some cool pictures. I know when I first got interested in astronomy, it was the cool pictures that really grabbed my attention. So at least I thought, you know, now that you've suffered through 15 lectures with me already, I thought it was time that I at least gave you some good some eye candy here. So this is the North American Nebula. You know, a lot of nebula are named in sort of sensible ways, like the Orion Nebula is in Orion. The Elephant Trunk Nebula, at least if you squint in the right way, looks like an elephant trunk, maybe. I confess, when I look at the North America Nebula, I am not creative enough to see North America in this case. I don't know if someone did. I don't know why it's named that. Maybe it was just observed in North America for the first time, and they decided to name it after that. So, but in any case, this happens to be in a star cluster with a really helpful name of IC 1396. So anyway, this is just another one that looks much cooler than its name would suggest. And you can go, there are gobs and gobs of these things. You know, as I said, you know, I appreciate you sticking with me through 15 lectures, so I thought I'd give you some eye candy here. But if you like these kinds of things, you can Google now and just find, you know, as many cool pictures as you want. So plenty to see out there. So let's say a little bit more about the interstellar medium, because I've said, you know, it's the stuff that's in between stars, and I've told you it's made of gas and dust. But what is that gas and dust, and how much is there? Well, it turns out that it's a lot more gas than dust, okay? About 99% gas and only 1% dust. So that's the first thing to remember. And this interstellar medium, it's everywhere in the galaxy, okay? So it pervades space, but it's almost nothing, you know, again. So it's this gas and dust, but, and we'll say more about what that gas is and what that dust is, but it's very low density. And now let's say exactly how low density. Well, a vacuum pump, and so I don't mean a vacuum cleaner, though a vacuum cleaner operates on the same principles, and I'm happy to talk more about that if you want. But a vacuum pump works by trying to suck all of the atoms out of some region of space. So if you go into a physics lab, there are lots of labs will use vacuum pumps, and the goal is to remove as much stuff as possible, ideally everything, but it turns out that we can't do that in practice. And the best vacuum that we can make so far has about 1 billion times more atoms than does the interstellar medium. Okay, so if you go into the best equipped lab in the world with the highest quality vacuum, you're still going to have 1 billion times more atoms in that essential nothingness than you have in the nothingness of interstellar space. So there really, it's, you know, we keep running into things that it's hard to wrap your mind around. It's really hard to wrap your mind around this, you know, I think, because there really is almost nothing out there. But it turns out that the very, very little that there is actually crucially important in some ways. In one of those ways is that's the nothing, that almost nothingness is the slight somethingness out of which stars are made. And so, but to give you just another means of comparison, because if you remember from the very beginning, when you have these sort of very hard concepts to wrap your mind around, hard numbers, huge numbers, very small numbers, one of the ways that we have to try to make sense of them is by means of comparison. So, you know, relative comparisons with things that we can relate to a little bit more. So, you know, one such comparison is here at the bottom. There are about as many atoms between your eye and the floor. If you just, you know, sort of, if you're sitting down, back up and look down at the floor, there are about as many atoms between your eye and the floor as there are in a column of interstellar gas that goes from the Earth to the center of the galaxy, which is 26,000 light years away. So, that's, you know, I said that's one way that you can help wrap your mind around things. I confess that's still so mind-boggling that maybe it just, further boggles you. But in any case, there you have it. So I've said that 99% of the interstellar medium is gas. What is the gas? Well, it probably won't surprise you to find that it's mostly hydrogen, right? The title of this lecture is the interstellar medium and star formation, right? So I've told you stars form out of the interstellar medium. I've also told you, if you remember, just a few lectures back, that stars are about 90% hydrogen. So it probably isn't a surprise, or if it's not, it shouldn't be, or if it is, it shouldn't be, that the composition of the interstellar medium is the same. So this gas that makes 99% of the interstellar medium is 90% hydrogen and about 10% helium. In reality, there are also trace amounts of some heavier elements, carbon, oxygen, and so on. We'll say a little bit more about that, but this should look familiar. The composition of the interstellar medium is the same as the composition of a new star, right? A newly born star, because as you know, the composition of a star changes over time due to the nuclear fusion processes. But this is it. So the interstellar medium is 99% gas, and of that gas, 90% of it is hydrogen, 10% is helium. And here's some more gratuitous eye candy. Lots of cool things. If you didn't love astronomy before, after 15 lectures, hopefully you at least have some aesthetic appreciation for it now. Okay, so what about this dust? And why do we even bother with dust? Well, because it's a class in astronomy, and so I have to come up with something to make you learn. And so I tell you that it's not just gas; it's also a little bit of dust. 1%, so not a lot. These grains are small. I say very small here. Again, that's relative to what? Well, it's relative to things that are bigger. Okay, relative to things that you would hold in your hand. Certainly, these are about the size of large molecules. So they're small relative to anything you can see with the naked eye, but they're large. They're certainly much larger than the gas, than the atoms of gas and the molecules of gas that we've talked about in the interstellar medium already. So most of the interstellar medium, right, is hydrogen gas. Well, hydrogen gas is really small, right? Hydrogen is the smallest atom in the universe. And so if it's an isolated hydrogen atom, then that's as small as it gets for an atom. If it's diatomic hydrogen, H2, then it's twice as big, but that's still really small. So relative to the hydrogen and the helium gas, these dust grains, we call them, are large. But they're much, much smaller than any dust that you see on your nightstand, right? So, we call them dust, but this is emphatically not the dust that's on your nightstand or underneath your bed. This is much, much smaller than that. You certainly can't see it with the naked eye. And it's composed of heavier elements. But of course, everything is heavier than hydrogen and helium, right? But it's got the usual assortment of sort of low abundance, but things that are out there atoms such as iron, silicon, and carbon. So that's what it is. Okay. Now, how do we know this, and why is it important? Well, one reason it's important is that dust absorbs short wavelength light. So the high energy, short wavelength, high frequency light, namely the ultraviolet and the blue end of the spectrum, that's going to be absorbed preferentially by dust. Whereas the longer wavelength light, the red and the infrared light, tend to pass through clouds of interstellar dust. And it turns out that's actually really important to understand because it makes an important impact on what we observe from Earth. So we said there's almost nothing out there, right? I made the claim that there are as many atoms in 26,000 light years of the interstellar medium as there are between your eyes and the floor right now, okay? But it turns out that a lot of stuff in the universe is really far away, okay? Even much, much farther than 26,000 light years, right? So even though the density of the interstellar medium is extremely low, a lot of stuff is so extremely far away that the net effect of the interstellar medium actually makes a difference, makes an observable difference, and impacts what we see. And so in this particular case, because the dust preferentially absorbs the ultraviolet and blue light, What that means is that a star that's very far away, which is emitting all wavelengths, if it passes through the interstellar medium, which it must on the way to us, it's not going to reach us with the same spectrum as it left the star, right? And so I think this slide shows it well, where you have all wavelengths emitted from the star, but as it passes through this dust of the interstellar medium, that dust pulls out the blue and the ultraviolet. Now, not all of it in reality, unless, I mean, it pulls out more and more the more interstellar medium it goes through. So if you go through enough of the interstellar medium, you will effectively have lost all of the ultraviolet and the blue end of the spectrum. If you go through just a little bit of the interstellar medium, then you'll still have some blue and some ultraviolet light left, but not as much as you started with. So it shifts the spectrum effectively towards the red end of the spectrum by doing this. And not very creatively, we call that interstellar reddening. And so, for example, if you start with a sort of a typical spectrum of a star, which you can see here on the left, has the characteristic black body sort of background structure, and then lots of more complicated structure on top of that by virtue of properties that we've talked about before, where the gas, the relatively cool gas for a star that's in the star's atmosphere will actually absorb some of the star's own light, and so lead to these absorption lines, for example. That's what's emitted, this emitted, that comes right out of the star. If you were standing just outside, or floating, I guess, just outside the star's atmosphere, that's what you would see. But after that passes through the interstellar medium, what we observe is very, very different. And you can see it down here. It looks nothing like all the spectra that I've showed you so far. We've gotten used to looking at black body spectra that all look kind of the same. They start off low and they peak somewhere, and then they kind of fall off, and then they have additional structure on top of it. That looks nothing like what we actually see, it turns out, for a far away object. Again, because if you're very close to us, relatively speaking, then there's so little interstellar medium to pass through that it doesn't make much of a difference. But if you look at a star that's far away, and you observe that through the interstellar medium, dust takes out so much of the star's light that what you get looks the spectrum is much lower, so the intensity is much lower, because even plenty of the red light actually gets filtered out. It's just that the red light gets filtered less well than does the blue light. So the whole spectrum gets pulled down, but the blue end of the spectrum gets pulled down more. And so if you don't know that, you would probably be really confused about what you were looking at. And if you tried to figure out properties of the star that emitted this light, you'd be totally wrong. Okay, so in a nutshell, that's why it's important to understand the interstellar medium, because unfortunately, all of the light that we see has come through the interstellar medium, more or less. Again, so for something that's relatively close to us, a nearby star, you can basically ignore the interstellar medium because there's so little of it between us and the star that it won't make a difference. But most of the universe is really far away from us, right? And so for most of the universe, we actually really need to worry about this. And so if you really zoom in on this, you can see, and note that the scale here on the plot at right is 1/10 that of the graph at left. So you've zoomed in and scaled things up by a factor of 10 in order to see this more, before you finally see that, yeah, this looks like something that you could call a stellar spectrum. And as I said, this is called reddening, or interstellar reddening. And again, it's not creative. It's just a way of telling you that what you see, the spectrum that you see, that you actually receive here on Earth, is redder. It's shifted towards the red end of the spectrum relative to what was actually emitted. And it's just because you've taken the blue parts out of the spectrum. So we talked about a different form of reddening earlier in the semester, in the context of Doppler shifts, right? So if a star is moving away from us, its spectrum will be Doppler shifted to the red end of the spectrum. This has nothing to do with that. It's completely different. It's just saying that because the light is traveling through the interstellar medium, the blue end of the spectrum is getting absorbed more strongly than is the red end of the spectrum. And so what actually makes it through that dust to us is bound to be redder on average than it was when it was emitted. There's something else to be aware of, though, another way that we can use this fact, if you will, because remember, we keep coming back to the fact that, we're interested in astronomy, we want to know what's out there in the universe, but we're basically stuck here on Earth, with a few exceptions of maybe going to the moon, maybe someday going to Mars, sending some space vehicles out, unmanned space vehicles out farther. Into the outer reaches of the solar system, for example. But basically, we're stuck here. And so we've identified, this reddening happens. That's a problem if what I want to know is actually what's really out there. But we should also ask the question, well, is there a way to leverage this? Is there a way to actually use this reddening to our advantage in some way? And there's one important thing that you can do, and it has to do with how you look through a dust cloud. Because I've told you that the interstellar medium is everywhere, but it's not homogeneous, right? It's not spread evenly throughout the universe. It's clumpy, okay? So there are parts of the interstellar medium that are even emptier than average, and there are parts that are denser than average, like the nebula that we've seen. So here's a particular picture of some region of space where you see lots and lots of background stars, and then all of a sudden there's just this black glob in the middle, this nothingness. So the question is, why on earth is there nothing there? Well, the answer is, it turns out there's not actually nothing there. What's actually there is a big cloud of interstellar dust, and it's in between us and these background stars. And so what's happening is that it's absorbing all that light. Okay, so you say, well, okay, now that we know that there's something, or even if you didn't know, if I hadn't told you, you might speculate, well, is there really nothing there? And now I need to explain some physics, reason that all of a sudden there would be some massive, sort of emptiness out in space, or is there something blocking the light and you'd like to know? Well, one way to do that, one way to answer that question is to look not at the visible light, but to look in a different part of the spectrum, in particular, looking at the infrared part of the spectrum. And the reason is that red light, and even more than red light, infrared light, travels through gas more easily than does the rest of the visible and certainly the ultraviolet part of the spectrum. So essentially what we've done here is said, well, we recognize this reddening effect. We recognize that the shorter the wavelength is, the higher the frequency is, the more absorbed, the more strongly absorbed the light is going to be by this gas cloud. So you say, well, if I want to see beyond the gas cloud, if this is in fact a gas cloud, right? If it's a gas cloud, then I'd like to see behind it. And in order to do that, I need to look at a wavelength that's going to actually make it through, right? And so the longer the wavelength, the easier it is for that light to get through. And so you say, aha, I need to leave the visible spectrum and I need to look in the infrared. And it turns out if you do that, you see a whole lot of stuff, right? It still looks a little lower density here, maybe, but the other thing is that I don't know what wavelength they actually looked at here, right? And even it's important to note that not all of the infrared light gets through either, right? It's a continuum in the sense that if you increase the wavelength even just a little bit more of that light will get through. So, this was on the right, the picture is taken in the infrared. I don't know, what wavelength specifically. If you looked at even longer wavelengths, then you would see even more, right? But this is a really powerful tool, and one thing that I've tried to stress throughout the series of lectures is that light is light, whether it's visible or not. The concept of invisible light is a little counterintuitive, but from a physics and astronomy perspective, there's no difference at all between visible light and infrared or ultraviolet, other than the energy, the wavelength, the frequency. But as far as like what it is, it has exactly the same properties. And it, in this case, infrared light has the great advantage of actually being able to make it through these clouds of interstellar gas. So if you want to see behind it, you construct a a telescope that's going to capture that infrared light, and you analyze that, and you can get a very different picture than what you would get just by analyzing the visible spectrum. So we've talked about interstellar dust absorbing things and the effect that that has. But it turns out that when it absorbs that light, it warms up, right? Light is energy. If you absorb that energy, you're going to warm up just like you do when you're outside in the sun. Well, interstellar dust also warms up, and as we've said over and over again, anything that's not at absolute zero temperature emits a black body spectrum, emits black body radiation. Now, most things that we encounter on a daily basis are not visible. They aren't hot enough to emit in the visible spectrum, right? That's why you need, again, night vision goggles in order to see a person, in the dark, in order to shift their black body spectrum into the visible range. Interstellar dust is exactly the same. It's certainly not hot enough to glow or to emit light in the visible spectrum, but it certainly is not at absolute zero, and so it certainly is warm enough to emit some black body radiation, and that's going to be in the infrared part of the spectrum. And so what's happening then is that these grains of dust out in the interstellar medium absorb visible and ultraviolet light that comes from stars just around them, and then because of that energy, it warms up, and now it gives off thermal radiation in the infrared. Okay, just through its own black body spectrum. And obviously different grains of dust at different places in the universe will be, in different parts of the interstellar medium will be at different precise temperatures. But a nice average temperature to think about the, grains of dust in the interstellar medium is around 100 Kelvin, right? So that's really cold for us. We would not want to be around 100 Kelvin. But it's actually quite a lot warmer than is just emptiness, the otherwise emptiness of space, and we'll talk more about that later. So now that we know that interstellar dust glows in the infrared, we can do something that's kind of cool, which is look at our own galaxy in the infrared. Okay, so we just look out at the galaxy and then filter out the visible and ultraviolet parts of the spectrum, leaving just the infrared. And obviously then we can't just look at it with our eyes because without doing a little bit more, because it turns out that looking at infrared light with your naked eye is really uninteresting because it just looks like nothing because your eye doesn't register it. So you collect that with a telescope, and then you use digital processing to render it visible in some way. And so this is a great image of dust in the Milky Way that comes from the IRAS infrared satellite. I confess I have no idea if it's actually pronounced IRAS or IRAS. I am otherwise unfamiliar with the satellite. But in any case, it gives us this cool picture where you clearly see the galactic plane, this very bright central line where that's where the galaxy is. We're looking edge on at the galaxy. But whereas normally we think of the galaxy as being very flat, and it is in general, has kind of the aspect ratio of a CD or a DVD. But when you look at it in the infrared, you see there's a whole lot more going on. There's a lot of dust out there, lying both above and below the galactic plane. Obviously, there's a lot of dust in the galactic plane too. That doesn't show up as well here. I mean, you do see the galactic plane, but it sort of stands out a lot, the stuff that's above and below. So, we'll talk more about galaxies going forward, and we will typically focus on the stuff that's in the galactic plane, because the vast majority of the mass and things, certainly the vast majority of visible mass is there. But it's important to know that there's plenty of gas above and below the plane as well. So as I mentioned a couple of times, we talk about the interstellar medium as a monolithic thing often. I mean, that's the implication when we just refer to the interstellar medium. But there's really a lot of variation in it. There are a lot of clouds in interstellar space, as you might imagine, and they have a very considerable range of temperatures and densities. So the densest clouds in the interstellar medium also happen to be the coldest, and they're known as giant molecular clouds. And the name suggests kind of what's going on here. They're giant, so they're really, really enormous things. And they're cold enough that they're capable of actually having not just atoms that exist, but molecules. Molecules, it turns out, are not bound very tightly. And so they usually get destroyed by starlight. So if molecules are close to a star, you know, the star's light will typically be enough to break those molecules up. And so the upshot is that if you want to find molecules in interstellar space, you got to go somewhere that's pretty far away from stars, because, you know, otherwise those molecules will be broken up. Now, when I say these are giant molecular clouds, I mean they're really giant. Again, it's all relative, but these things can be 100 light years sort of in scale. So, you know, they're small on the scale of galaxies, you know, which, again, say the Milky Way is 100,000 light years across, but, you know, 100 light years is still pretty big. So, you know, I've said that these things consist of molecules. Well, what molecules? Well, you might, if you know, it might not have been a bad exercise to let you sit and think about it for a little bit before I plaster the answer up here. But the answer probably is not going to surprise you. The most common molecule is diatomic hydrogen, which is not a shock because the by far the most common atom in the interstellar medium is hydrogen, right? So if you've got mostly hydrogen atoms, when you start forming, you know, multi-atom molecules, you're going to get mostly hydrogen molecules. But there are other atoms out there, right? There's carbon, there's oxygen, and you get various combinations of those, carbon monoxide, methanol, you know, and others. Over 150 different types of molecules have been observed in the interstellar medium. And of course, the only way that we observe these is by looking at spectra, right? It's not like we go out on a starship into interstellar space and, you know, collect a big, you know, sort of flask of this stuff and then come back to Earth and analyze it. All we can do is look at the spectra coming out of these clouds. And so people have done that and identified a whole lot of molecules. We're certainly not going to study those in detail, but here are a few of the more common ones. Okay, and it turns out that just like we can look in the infrared, you know, I showed you a couple of slides back, the Milky Way in the infrared, you can actually look at specific wavelengths that are characteristic of specific molecules, right? And so here's such an image looking at carbon monoxide emission lines in particular. And so in other words, you take all of the light that comes to you and you filter out everything that isn't specifically in the carbon monoxide spectrum. Because just like every atom has a unique set of atomic energy levels, and so has a unique set of transitions, which means a unique set of spectral lines, you know, unique wavelengths that it absorbs and emits. The same is true of a molecule. Carbon monoxide, in this case, has a specific set of molecular energy levels. Transitions between those energy levels give a specific set of frequencies of light and wavelengths of light, and so we filtered out everything except for that. And so here you see, where is the carbon monoxide in the universe, or not in the universe, but in the galaxy. And so you see, again, it's largely around the galactic plane. Makes sense. That's where most of the stuff, you know, of any kind of stuff in the galaxy is. But you see stuff, you know, above and below the plane as well. And so you can compare, you know, these pictures, and you can see there's some similarities and there's some differences, and people spend a lot of time studying that. And so we aren't going to spend a whole lot of time studying that in this class, but going forward, if it strikes your fancy, there's plenty to learn there. So now that we know there are these giant molecular clouds out there, let's think about what happens to them. Okay, because and you know, we've kind of telegraphed the plan here with the title of the lecture again, the interstellar medium and star formation. But let's imagine ourselves watching this giant molecular cloud, which again is essentially it's the coldest, densest thing that exists in the interstellar medium. So it's far away from other stars, and gravity is going to do its thing, right? Gravity it's always an attractive force. You've got this mass in interstellar space. It's very low density relative to anything that we interact with here on Earth, but it's much higher density than most of the interstellar medium. And so it's going to take a while, but gravity is going to make this thing even denser, right? Gravity is going to pull this to get the cloud together into smaller and smaller volumes. And if it happens to reach a critical density, then gravity is going to win, if you will, over the gas pressure. Because if you remember back when we talked about stellar equilibrium, we said, well, gravity is always trying to collapse the star, and what maintains the stellar structure against that collapse is the internal pressure that's generated by, well, light in the case of a main sequence star that comes from the nuclear fusion reactions. So in a giant molecular cloud, you've got the same type of dynamic. You've got gravity tending to make it collapse, and you've got this gas exerts a pressure, just like the atmosphere exerts a pressure. And so there's this balancing act. But if there's enough density, then gravity is going to win, okay? And it's going to be victorious over this gas pressure, and the cloud is going to start to collapse. Now, as this cloud collapses, it's not going to do so uniformly. So, we talk about the interstellar medium as if it's a thing, but really it's lumpy, right? You have giant molecular clouds some places, and then you have almost nothing other places. Well, even within this giant molecular cloud, as it's collapsing, it's not going to collapse completely uniformly, right? There are going to be parts of that cloud that end up collapsing more sooner than others, just by statistical variations. And so each one of these fragments is going to further fragment and continuing to collapse. And the upshot is, to kind of cut to the chase, individual stars are going to form within this molecular cloud at very similar times. Okay? The cloud as a whole is collapsing, but you're going to get sub bits of that cloud that are going to collapse faster than others. And that's where stars are going to be formed. Okay? So it's an interesting situation where you started out with no stars in this giant molecular cloud, or very few. It's far away from stars, right? Because otherwise it would be too hot to be a molecular cloud. So on the one hand, you have to start off in a very cold situation. But then as gravity makes these things collapse, they collapse fast enough and significantly enough that they get these molecular cloud cores that actually become dense enough to form stars themselves. And so the result is that you get a cluster of stars that forms together out of the same giant molecular cloud and at essentially the same time. Now, I don't mean within like minutes or seconds or even just a few years of one another necessarily, but on an astronomical time scales, basically all of these stars are going to be forming at the same time. And that's actually useful information for us, because then we can look at those stars and see, well, how many M-class stars are there, how many O-class stars are there, and we can sort of analyze them knowing that these stars all formed at essentially the same time. So here's an example of a star cluster with the inspiring name of NGC 290. Image taken by the Hubble. Takes lots of, I won't say all of the best pictures, but a lot of the best pictures come from the Hubble. And so, I showed you some nebula earlier. This is this lecture probably has the best set of images of any lecture this semester. But I won't guarantee that, because I want you to come back and see future lectures. And just to reiterate, all of these stars were born at, I say the same time, very similar times here, and born from the same material, right? So, I said the interstellar medium is made of gas and dust, and that gas is mostly hydrogen, a little bit of helium. There's some slight variations from cloud to cloud in different places in the universe. for some reasons that we'll talk about. But when you look at a star cluster, you know that all of these stars form from a single giant molecular cloud at very similar times and out of the same material. So that really is useful, because it's the kind of thing that you might do if you could do an astronomy experiment, right? Astronomy, one of the challenges is that it's primarily observational, right? We're stuck here on Earth. We're stuck with what's out there. We observe what we can. But as scientists, no doubt there are things that we would like to analyze, like to look at, that we can't, just because they happen not to be there. And you can't just like make a star in your garage. But in this case, it's about as controlled a situation as you can have in astronomy, where you know all these stars were born at the same time from the same material, and so any variations in stellar properties then are not due to when they formed. They're not due to what they formed from. They're due to something else, and so that's useful information. And more gratuitous eye candy. The galaxy is it's full of star clusters, and so these are things that you don't see with your naked eye, like this anyway. You don't typically see with a backyard telescope, but thanks to your taxpayer dollars, we got things like the Hubble, and so you might as well enjoy the pictures that it beams home. So let's now say a little bit more about individual stars in that cluster. So the first thing that I want to say is something that I've mentioned before in the context, I think, first of solar system formation, even at the little that we said about that in the beginning of the semester, but it's certainly true of stars as well. As things start to collapse, they never collapse perfectly symmetrically. And so the result is that they're always rotating a little bit. And just like an ice skater, when she pulls her arms in, she speeds up in terms of the rotation. That's exactly the case for stars too, due to conservation of angular momentum, if you're keeping track. So the result is that as the cloud collapses, the rotation rate increases. And it turns out that things that rotate tend to flatten too, at least if they're not solid, right? Which this is not. And so what happens is that you get a central ball that forms, and then you get kind of a pancake that a disk, circular disk that tends to surround that central mass. So that central mass initially is known as a protostar. So it's not yet a star. Remember, what defines a star is nuclear fusion in the core, so that it hasn't gotten hot enough and dense enough for nuclear fusion to occur yet. But it is heating up because you're converting that gravitational potential energy into heat. So it is heating up, it's increasing its rotation rate, and you have this disk of gas that surrounds it. So over time, the protostar continues to collapse, and the disk starts to take on some additional structure because gravity is acting in the disk too. Just like the cloud itself was not uniform, right? There were clumps of it, it was clumpy, right? There were parts of it that were a little bit more dense, and there were parts that were a little less dense. Well, that's true of this disk surrounding the protostar as well. And so the result is that there are parts of the disk that are a little bit more dense, have a little bit stronger gravity than other parts of the star, and so they tend to they tend to attract other parts of the disk. And so the disk ends up breaking up into rings. And eventually, those rings end up coalescing, and that's how planets form. And so, this is a class in stars in the universe, so we spend the vast majority of our time talking about stars in the universe. But, we're talking about star formation here, and it turns out that solar systems form right alongside the star for exactly this reason. And so, just like we said that the stars in a star cluster form at the same time out of the same material, well, the planets in a solar system form at the same time out of largely the same stuff, and I'll say caveat that because I'll come back to that, but as the star. So they form at exactly the same time as the star, which is useful because if you happen to be on Earth where you can actually do experiments and figure things out like how old is the Earth, well, then that tells you, essentially how old the star is as well. Now, I said that planets form out of the same stuff, as the star here. So you might be tempted to say, well, okay, why on earth is the Earth made of such different stuff as the sun, right? If you remember back just a few lectures ago, we talked about in the early 1900s when the first detailed analysis was done on stellar composition using spectral analysis, and they discovered that it was made almost entirely of hydrogen and helium with some other things. And we talked about how those results were not immediately received or accepted because it was just so far away from the expectations, namely that the sun will be made of more or less the same stuff as Earth. Well, as you can see, when the star is first forming, the stuff is relatively well mixed. The gas, as it collapses, it is initially fairly well mixed. But as it, this process, we've skipped a whole lot of time here, right, between A and D. These things do not happen overnight. And so just like things, I said, again, these gas clouds are lumpy. Well, there's lumpiness at every level. These rings are a little lumpy too. And so some things are heavier than others. And as a result, what you end up with is, as you see in our solar system, we have rocky planets that are closer to the sun, right? Higher density material on the surface anyway. And then the gas giants are farther out. So in the end, you do get some variations in composition, certainly. But it's, as I said, it's useful to know that the solar system forms at exactly the same time as the central star. Now, it's hard to see a protostar in real life. So not that it's impossible. We have seen stars form, but it's rare, right? On the time scales of our lives, it's rare to look out in the universe and actually see a star forming. But that doesn't prevent artists from rendering their concepts, and it would be pretty cool to actually watch this happen, I think. So, as I said, we do have some real ones, and actually the artists, sometimes artists take liberties. In this case, the renderings are actually pretty accurate. Though I confess, full disclosure, if I were to look at these pictures outside of the slide, if I didn't already know what they were, I am not specialized enough to look at that and say, aha, protostar formation, or protostar, nearing stellar formation, but that's what they look like. So now let's say a little bit more about what the protostar does, and as take another step towards actual stellar formation. So thanks to gravitational collapse, again, you've got this central ball. Again, it's a gas, right? So it's not a hard sphere by any means, but you have this central ball, and material, thanks to gravity, is moving in towards the protostar in something that's known as an accretion disk. So to accrete just means to collect mass. And so an accretion disk is just a disk of mass that is spiraling into a central mass. We'll talk more about accretion disks in the context of black holes as well near the end of the semester. But right now we're here with protostars. And so on the one hand, material is flowing in to the star, kind of spiraling in the accretion disk. But there are also these features known as bipolar jets, which are what they sound like. You have jets that kind of squirt material out in either direction perpendicular to the plane of the accretion disk, and then you also get some outflows along the accretion disk. So this process is actually quite complicated, and people can and do spend careers modeling this on supercomputers. And so if you're interested in that, there's plenty of people doing that, plenty of work, in that area. Now, we talk about structure, we talk about lumpiness of gas clouds and formation of star clusters, for example. Well, it turns out that you can also have situations where two stars form just very close to one another. And if they're close enough, then they may become gravitationally bound to one another, right? And we've talked about binary star systems, and this is how they form. So Typically, these stars are not equal masses, right? It would kind of be random if they were. So typically they're not. And so here on the left, we actually have a radio wave image of a real binary star system forming. So we don't see a lot of these. This is not a daily observation, but we have seen it. And so you have a primary star, which is more massive, and then you have a secondary star, which is smaller. And then you have what's called a circumbinary disk, which just means the disk of material that's kind of surrounding it. That may evolve into planets later on, But it turns out, I told you that people spend their career simulating these things. It turns out that on the right, we have a computer simulation of the same star system, and you can see it gets it pretty well, right? Pretty good agreement, at least visually there. So they're structured at each level, just like if you were with us in the very first lecture, we looked at starting out something like 10 million light years from Earth, and then zooming in and seeing the structure at each scale. Same thing here. You've got lumpiness at each scale, and at least very often it leads to multiple star formations in the same neighborhood, so that they actually are gravitationally attracted to one another enough that they sort of form that bound state. So now I want to talk about a question that may or may not have occurred to you, but that is, why do we see protostars at all? I showed you a picture just a few slides back of a protostar, but I've also told you that it's a protostar. It's not a star, right? We know where stars' light comes from. We know why it shines. It shines because it's really hot, right? You've got nuclear reactions going on in the core, releasing huge amounts of energy that heat the star up. Thanks to being hot enough, the Boltzmann distribution, the black body spectrum that it gives off is well in the visible range, and so that's why you see a star. But a protostar is not a star, right? A protostar does not have nuclear fusion going on in its core. So why does it shine? So that I can take a picture of it and show it to you. Well, it turns out the answer is, as with so many things in astronomy, gravity. So as the protostar collapses, you are giving up gravitational potential energy. It's just like dropping a rock. As if you hold a rock out or whatever you have and you drop it, it speeds up as it falls. You give it gravitational potential energy in the beginning, and that gravitational energy through the action of the gravitational force is converted into kinetic energy. Well, the same thing happens in the case of protostellar collapse. So if you have a cloud of gas, gravity makes it collapse. Well, as it collapses, it speeds up. The molecules and the atoms in that gas collide with one another, and through those collisions, they convert that gravitational potential energy into heat, which, if you remember back, temperature is just a measure of the average kinetic energy of the atoms or molecules, which is, the average speed of those molecules. So as they collapse, they speed up, they bump into one another, they heat up, and they get hot enough to shine. So it's not nuclear fusion in the core yet that's heating up the protostar. It's actually just the conversion of gravitational potential energy into thermal energy, heat, which actually makes it able to shine. Eventually, though, it gets hot enough, if it does, right? This doesn't have to happen, but if there's enough mass, then it will get hot enough in the core for nuclear fusion to finally be initiated. And if that ignition occurs, if you can ignite the core, then it goes gangbusters, right? Then a true star is born. The mass of that star heats up very quickly, and then it continues radiating in the visible spectrum. So ignition is that moment in time, is that phenomenon where the nuclear fusion finally starts to occur. And once it does, it releases so much energy again that it quickly heats up the rest of the material. So now let's come back to the HR diagram. We're bringing all everything together. I told you that the first third of the class was kind of background and build up sort of a knowledge base, and then we'd really get into the meat and potatoes. We talk about stars. Well, we're well into our discussion of stars, but now we're going to tie in stellar formation with the HR diagram. So if you remember the HR diagram, you have this sort of this diagonal, not quite line, but certainly it looks more, mostly linear on this plot, representing the main sequence. And I haven't shown you, for simplicity, I've taken off the giants and the white dwarfs here because we want to focus on protostars. Well, protostars lie in the upper right-hand part of the HR diagram. Okay, because they're big. Okay, because gravity hasn't fully collapsed them yet. But they can actually, it's kind of interesting, and this may come as a surprise to you, they can be quite luminous. I mean, so if you look at these different tracks are sort of progressions of protostars as they turn into full-blown stars for different masses. So these are low-mass protostars over here, and these are high-mass protostars here. So this one happens to be 60 solar masses, and this one down here is 0.8 solar masses. So you can see they take different tracks based upon their mass, which is consistent with what I've said before, which is that almost all of the properties of a star are determined by its mass. Okay, so but they can be quite luminous. I mean, you look at this again. The vertical axis is given in units of solar luminosity. So a value of 1 means it has the same luminosity as the sun. You look at a 0.8 solar mass protostar. Well, its luminosity is 100 times the sun's luminosity, and it's not even a true star, right? And in fact, what's interesting about these low mass protostars is that their luminosity almost uniformly falls as they become, as they transition into true stars. And so you might want to think about that for a little bit, why that would be. But essentially, it's just because it's heating up as it gets smaller, right? So as it heats up, all other things being equal, the luminosity will go up, right? Because hotter things with higher temperatures give off more light, according to the Stefan-Boltzmann law, right? But on the other hand, as it collapses, the surface area gets smaller, and so all other things being equal, a smaller surface area gives off less light, just because there's less light and less surface to radiate. So you have these competing effects, and it's clear that for a low mass star, the net effect is a very strong reduction actually in the overall luminosity. On the other hand, for high mass stars, the protostellar path on the HR diagram is almost perfectly horizontal. So in that case, those two effects essentially cancel each other out. So the increase in temperature more or less exactly balances out the decrease in the radiating surface area, and so those paths are essentially perfectly horizontal, at least up until the very last second. So there's a lot of interesting things here. I think I hope you think, but that's what it looks like for protostars as they enter or as they approach the main sequence. They follow trajectories that depend upon their mass, and eventually, once they reach the point of ignition, then a star is born and it joins the main sequence. So this path, the path that a protostar takes on its way to the main sequence, has a name. It's known as the Hayashi Track, and it's just this: it's the location of the protostars and the path they take on the HR diagram before they're hot enough to actually undergo that nuclear fusion that defines being a star. So this is the first thing that we've seen in terms of, we've talked about the HR diagram before, but this is the first time that we've seen movement on the HR diagram, right? But it's not the last. We're going to see plenty more of that. This is the birth of a star. And if you hold on over the next several lectures, we're going to talk about the evolution of stars. And so it turns out that joining the main sequence is by no means the end of the story. There's plenty more to come. And so hopefully you'll stick around for that. It's also worth noting that the sun, for example, we like to start with the sun because it's our favorite star. It's the one we know the best. It spent about 30 million years on the Hayashi Track, and we know that from simulations. So it takes 30 million years to sort of move from the beginnings of gravitational collapse of that star to actually joining the main sequence. Once on the main sequence, the sun is going to stay there quite happily for about 10 billion years. So comparatively speaking, the Hayashi Track is a very quick event. It happens, the star moves very quickly on that relative to the star's main sequence lifetime. Now, relative to your lifetime and mine, it's obviously a different story. But the result of this is that because it happens so quickly, in astronomical timescales, observing a protostar is very rare. You would really have to be looking at exactly the right place at the right time to catch this thing happening. And here's just another sort of schematic of the Hayashi Track. So now think about the following. Why would a protostar become less luminous as it approaches the main sequence? And if this sounds familiar, it should, because I basically asked you this and answered it very recently. And the answer is, and this is also, if it feels like I'm saying this a second time, that probably means it's likely to show up on a quiz or something. But the answer is it's shrinking, right? As it shrinks, it's heating up, but it's also, getting the surface area is decreasing. And so as we saw, for the more massive stars, those effects basically cancel each other out. For low mass stars, though, the surface area effect dominates, and so the luminosity actually goes down. So again, it seems counterintuitive, but you can drop in luminosity by a factor of 100 as you form a real star. So, I made a comment a few slides ago that this is how stars form, but I made the statement that if it joins the main sequence, then this is what happens. Well, it turns out that gravity will work on a ball of gas that is not massive enough to actually become a full-blown star. Okay, so protostars of masses that are lower than about 8/100ths or 8% of a solar mass are just too small, and they will never join the main sequence. Okay, and again, the reason is straightforward. As the thing collapses, it heats up, but how much it heats up depends upon how much mass you have. And so if you don't have enough mass, you won't get hot enough in the core, and you just won't be able to actually begin the proton-proton chain and fuse hydrogen to form helium. And so you're going to have, in that case, not a star, but a failed star. And we have a fancy name for a failed star, and we call those things brown dwarfs. So if you've ever heard of a brown dwarf, all it is a failed star. If you haven't heard before of a brown dwarf, it turns out it's still a failed star. Okay. But why do we see brown dwarfs at all? And as their name suggests, they're kind of brown. By brown, what we mean is it's actually hard to see. But you can see them, otherwise we wouldn't know they existed, presumably. And what happens is that they do get hot enough, or they may get hot enough, to fuse hydrogen into deuterium, actually. They may get hot enough to do the first step in the proton-proton chain, but they do not get hot enough for all of the steps of the proton-proton chain to take place. And so the result is that you get a little bit of energy release in the formation of the deuterium. You get a little more energy release in the annihilation of the positrons with electrons, but you don't have enough thermal energy to form the helium-3 or the helium-4. And so what happens is you get a little bit of energy release, but otherwise that brown dwarf, that want-to-be star, radiates off its thermal energy into the cosmos and eventually just cools down. And I don't know if I can use the term dies because it was never quite born as a star, but eventually it just cools off and disappears. So, you know, if you were hopeful that a brown dwarf was enough to just give a classification as a brown dwarf, you know, no doubt at one point in time it was, but that time is not now. So just like we have different classes of stars, we have a few classes of brown dwarfs of different temperatures. And just like with stars, those temperatures depend upon the mass, right? Because the reason these things got warmed up is because of the gravitational energy, right? And so first, the protostars are shining because of the conversion of gravitational potential energy into thermal energy, which leads to visible black body radiation. In the case of brown dwarfs, you may get some nuclear fusion reactions, but not the full proton-proton chain, so that may maintain the temperatures. And so the three main classes of brown dwarfs are L, T, and Y, and they have these particular temperatures associated with them. And so if we want to kind of complete our stellar class line and kind of tack on brown dwarfs to the end, we can do that. Again, they're not true stars because they don't have the sort of full-blown self-sustaining nuclear reactions occurring in the core. There may be some nuclear reactions, but not the full collection. So that's a brown dwarf. And that brings us to the end of this lecture, of the first of part 2 of the course, as we sort of continue on with stellar formation now, and we will, over the course of the next several lectures, talk about the evolution of stars. So we saw the first bit today in the context of protostars traveling down the Hayashi Track. And I do want to be clear, when I say traveling down the Hayashi Track, this is not a physical traveling, right? The star it's collapsing as it does that, but it's not moving through space. Or if it is, that's not relevant to to this. But it moves through, on the HR diagram, sort of moves down the Hayashi Track. Eventually, either is massive enough to form a true star and join the main sequence, or not massive enough, and it kind of lives for a while as a brown dwarf. So thanks for sticking around. I hope you learned something, and hopefully you'll come back for lecture 17, where we will continue studying the evolution of stars and their further movement on the HR diagram. So I hope to see you there.